In episode 40, titled WireGuard in Hybrid, Why It's Referenced and When It Fits, we treat WireGuard as a modern virtual private network option that emphasizes simplicity and speed because those two traits are often the deciding factors in hybrid environments where teams want secure connectivity without a sprawling appliance footprint. The exam may reference WireGuard less as a brand and more as a signal that the scenario values lean design, strong defaults, and manageable operations. Many organizations already have traditional virtual private network appliances and mature policies around them, so the best answer is not always the newest tool. But WireGuard becomes relevant when the environment needs secure links that are easy to deploy, easy to reason about, and efficient under load. Hybrid scenarios amplify this need because connectivity often spans small sites, remote administrators, and cloud segments where complexity multiplies quickly. The goal is to understand what WireGuard offers conceptually, what problems it solves well, and what operational responsibilities still remain even when the protocol itself is small and clean. When you can explain those trade-offs, you can choose it confidently when it fits and avoid it when it introduces mismatches. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Conceptually, WireGuard is a lightweight protocol using strong cryptography and a small codebase. And those traits matter because they reduce attack surface and reduce operational friction compared to more complex stacks. Lightweight here means fewer moving parts in the protocol design and fewer configuration knobs that can be set inconsistently across peers. Strong cryptography means modern algorithms and a design that aims to make secure behavior the default rather than an optional mode, which aligns well with secure by design exam language. A small code base matters because it is easier to audit, easier to maintain, and often easier to reason about during troubleshooting, which reduces the chance that a misconfiguration hides behind complexity. None of this makes it magically perfect, but it does make it a good fit when you want a secure tunnel that behaves predictably and does not require extensive protocol negotiation. In exam reasoning, references to simplicity, speed, and clean deployment often hint that a lightweight approach is preferred, especially for narrow use cases. The key is to treat WireGuard as a tool that reduces complexity in the tunnel itself, while still requiring disciplined planning around keys, routing, and monitoring. A common fit is point-to-point secure links and remote access, because WireGuard's peer-based model aligns well with connecting a small number of known endpoints securely. Point-to-point links include connecting two small sites, connecting a branch gateway to a cloud host, or connecting a management jump host to a protected network segment. Remote access fits when individual administrators or devices need secure access to a limited set of internal resources without deploying heavy client stacks or complex gateways. The peer model works well when you can define a set of trusted peers and the allowed traffic between them, because the configuration becomes explicit and stable. In hybrid environments, this can be attractive for targeted connectivity, such as linking a monitoring system to a remote site or providing secure access for a small operations team. In exam scenarios, when the requirement is narrow, such as connect these two endpoints securely, WireGuard can be a plausible best answer because it matches the simplicity goal. The key is to recognize that WireGuard is excellent at clean point-to-point and small mesh designs, but it is not automatically the best answer for large enterprise remote access programs without additional management tooling and governance. A strong guiding rule is to use WireGuard when simplicity, performance and manageability matter, especially when the scope is limited and the operational model is clear. Simplicity matters when teams are small, when deployment must be fast, or when traditional virtual private network appliances add cost and complexity disproportionate to the need. Performance matters when the tunnel must carry meaningful traffic volume, or when latency and throughput are important for the workload, and lightweight behavior can help reduce overhead. Manageability matters because hybrid environments already have enough moving parts, so adding a tunnel that is straightforward to configure and monitor can be a practical advantage. The exam often rewards solutions that meet requirements with fewer dependencies, and WireGuard is often referenced in that spirit. The caveat is that manageability also includes key lifecycle, peer inventory, and configuration discipline, because a simple protocol does not remove the need for operational governance. In scenario logic, the best answer is the one that meets security and connectivity goals with minimal complexity, and WireGuard can fit that role when the environment supports it. Key management remains essential because secure distribution and rotation of keys is still the heart of trust, and strong cryptography is only as good as the way keys are handled. WireGuard's simplicity can create a false sense of safety if teams treat key distribution casually, because losing control of a private key can grant an attacker tunnel access that looks legitimate. Secure distribution means keys are generated and stored safely. Access to private keys is restricted, and provisioning processes ensure that only authorized devices receive credentials. Rotation matters because long-lived keys increase risk over time, especially when devices are replaced, staff changes occur, or incident response requires rapid revocation. Key revocation also needs a plan because removing or changing keys must be done cleanly so that access is removed without breaking legitimate connectivity unexpectedly. In exam scenarios, when a solution mentions strong encryption, the best answer often also includes key lifecycle thinking because governance is part of security. The key is that WireGuard reduces protocol complexity, but it does not reduce the need for disciplined trust management. Routing in WireGuard is often described through interfaces and allowed Internet protocol lists, and understanding that model helps avoid common hybrid routing mistakes. Each peer relationship effectively creates a tunnel interface, and traffic that matches defined allowed address ranges is sent through the tunnel to the corresponding peer. This means allowed addresses serve two purposes. They define what traffic is permitted to traverse the tunnel, and they influence routing by determining which destinations are associated with which peer. In a simple point-to-point design, this mapping can be straightforward, but in hybrid networks with multiple peers and multiple internal subnets, the allowed address sets must be planned carefully to avoid conflicts and ambiguous paths. The model is powerful because it makes intent explicit, but it is also unforgiving when misconfigured because the tunnel may silently drop traffic that does not match allowed ranges. In exam terms, when the scenario involves small site connectivity and specific subnets that must be reachable, the allowed address model is a clue that routing control is part of the design. The key is to treat allowed address configuration as both a security policy and a routing policy, because it performs both functions in practice. Consider a scenario linking two small sites without complex virtual private network appliances, such as two offices that need secure access to a shared application, and the organization wants a simple, cost-effective solution. In this case, a peer-based tunnel between two gateways or hosts can provide encrypted connectivity with clear intent about which subnets are reachable. The deployment can be straightforward because it does not require heavy infrastructure, and it can be operated by a small team if documentation and key management are handled well. This is especially attractive when the sites are stable and the routing needs are simple because the configuration does not change frequently. The design still requires attention to monitoring and failover expectations because a single tunnel is a dependency and should be observed like any other. In exam reasoning, this scenario often favors a simpler tunnel approach because the requirement is narrow and the operational model is limited. The key is that the solution aligns with constraints, small scale, clear endpoints, and a preference for minimal moving parts. A common pitfall is misconfigured allowed Internet protocol ranges, creating routing leaks or black holes, because the tunnel may capture traffic that should not go through it or may fail to carry traffic that must. If the allowed ranges are too broad, the peer may accept traffic that was never intended, potentially exposing internal networks or diverting traffic through an unintended path. If the allowed ranges are too narrow, required subnets may not be reachable, causing timeouts that look like application issues even though the tunnel is up. Misconfiguration can also create overlapping definitions across peers, where the same destination range appears under multiple peers, leading to ambiguous routing and unpredictable behavior. In hybrid contexts, these problems can be subtle because some paths work and others fail, depending on which subnet is involved and how routes are selected. Exam scenarios that describe tunnel is up but traffic is black-holed often point toward allowed range mistakes. The best answer typically involves correcting allowed ranges and ensuring routing intent is consistent and documented. Another pitfall is poor key handling undermining strong cryptography benefits because the protocol can be designed securely and still be compromised through weak operational practices. If keys are shared casually, stored insecurely, or reused across devices, the risk of credential compromise increases and revocation becomes difficult. If offboarding is weak, former administrators or decommissioned devices may retain valid keys, creating persistent unauthorized access paths. If incident response does not include key rotation capability, a suspected compromise can linger because the organization cannot quickly invalidate tunnel trust. These failures are operational, but their impact is security critical, which is why the exam often expects you to treat key lifecycle as part of the design. The correct answer is usually one that pairs strong cryptography with strong handling, because cryptography without governance is fragile. The key is that the tunnel's strength is not only in its algorithms, but in the discipline of its trust model. There are quick wins that keep small WireGuard deployments healthy, such as documenting peers, rotating keys, and monitoring handshake status, because these practices preserve clarity and reduce silent failure risk. Documenting peers means you maintain an inventory of who is connected, what networks each peer is allowed to reach, and who owns the peer, which prevents drift and speeds troubleshooting. Rotating keys reduces the risk of long-lived credential compromise and provides a practiced process for revocation and renewal. Monitoring handshake status and connectivity provides early warning when a peer becomes unreachable, when a path changes, or when a key mismatch occurs, which reduces the chance that failures are discovered only when business services break. These practices are simple, but they are powerful because they address the main operational risks of peer-based tunnels: stale configuration and unmanaged credentials. In exam reasoning, answers that include monitoring and key lifecycle tend to align with best practice because they treat the tunnel as a managed service rather than a one-time setup. The key is that simple systems remain simple only when they are maintained deliberately. Interoperability matters because platform support varies across clients and servers, and the best design considers whether endpoints can actually run the chosen tunnel technology reliably. Some environments have strong support for WireGuard across common operating systems and network platforms, while others rely on legacy appliances, managed endpoints, or constrained devices where support may be limited or operationally awkward. In hybrid contexts, you may need the tunnel on a cloud host, a branch gateway, and administrator laptops, and the solution must work across all three without fragile hacks. If platform support is inconsistent, the best tunnel protocol on paper can become a support nightmare, which undermines the simplicity goal. Exam scenarios sometimes hint at this by describing mixed endpoint types or strict enterprise tooling requirements, which should influence whether a lightweight peer tunnel is feasible. The best answer usually fits the organization's ecosystem rather than requiring exotic exceptions. The key is that a tunnel is only useful if the endpoints can run it reliably and if operations can support it at scale. A memory anchor that helps keep this topic straight is simple, fast, peer-based, key management matters because it captures both the attraction and the responsibility. Simple and fast describe why WireGuard is referenced, especially in scenarios that value minimal overhead and straightforward deployment. Peer-based reminds you that the trust model is explicit between endpoints, which makes configuration clean but requires careful mapping of allowed ranges and peer inventory. Key management matters reminds you that the strongest algorithms do not help if private keys are mishandled, shared, or never rotated. This anchor helps you choose correctly in exam questions because it pushes you to mention both fit and governance, which is often what distinguishes a correct answer from an incomplete one. It also keeps you from treating WireGuard as a magic fix for complex remote access programs where centralized identity integration and large-scale policy management may be more important. When you can recite this anchor, you can justify the choice and the safeguards succinctly. To end the core, choose WireGuard or a traditional virtual private network and justify it using the constraints stated, because this is where exam logic tends to land. If the requirement is a small number of secure point-to-point links, limited operational overhead, and strong performance, WireGuard can be the best fit because it delivers secure tunnels with minimal complexity. If the requirement is a large remote access population with complex role-based access, deep integration with enterprise identity, and mature centralized governance, a traditional remote access solution may fit better because it provides broader management capabilities even if the protocol is more complex. If interoperability constraints exist, such as endpoints that cannot support WireGuard cleanly, that constraint can override the simplicity advantage. In either case, the best answer will include key lifecycle discipline and monitoring because both tunnel families require trust management and operational visibility. The exam rewards you for matching the tool to the scale and governance reality rather than choosing based on novelty. When you justify based on constraints, your decision becomes defensible and consistent. In the conclusion of episode 40, titled WireGuard in Hybrid, Why It's Referenced and When It Fits, WireGuard is referenced because it offers a modern, lightweight approach to secure tunneling that emphasizes simplicity and strong cryptography, making it a strong fit for point-to-point links and limited-scope remote access in hybrid environments. It works well when performance and manageability matter, and when the peer model aligns with the environment's scale and operational maturity. Key management remains essential because secure distribution, rotation, and revocation determine whether the tunnel remains trustworthy over time. Routing behavior depends on interface design and allowed Internet Protocol lists, so misconfiguration can create leaks or black holes. And monitoring handshake status and documenting peers are practical safeguards. Interoperability should be considered because endpoint platform support can determine feasibility as much as protocol elegance. Assign yourself one peer configuration narration by describing, aloud, which peers exist, which address ranges each peer is allowed to reach, how keys are distributed and rotated, and how you would detect a failed handshake, because that narration is the practical thinking the exam is trying to develop. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.